Alright, so it's asking you to figure out the following problem. The problem reads that aluminum metal reacts with a solution of copper 2 chloride to give copper metal in a solution of aluminum chloride. This is going back to writing the reaction. So let's go ahead and pull out the important information. And we know that we're going to be using the following, where percent yield is found by finding actual yield divided by the theoretical yield. Now, some of you guys ask me, what am I finding the theoretical yield of? Well, the problem is, they didn't give you a balanced reaction. So it's kind of a difficult problem if you don't write the balanced reaction. You got 5 seconds to move yourselves. I'm going to write you off if not. Okay, so it says aluminum metal. It's reacting with a solution of copper 2 chloride. The phrase reacts with is essentially your plus sign. Solution of copper 2 chloride. Copper we know is going to be Cu. Chloride you know is going to be Cl. As far as the charges are concerned, the Roman numeral tells you the charge at the top. Chloride you know from the periodic table is -1. When you crisscross it, you're going to end up with CuCl2. To give is essentially your arrow. If it says copper metal, again, it's without the charge, so it's just going to be Cu. In a solution of aluminum chloride, aluminum we know, and chloride we know. Aluminum has always a charge of +3. We know that from the periodic table. Chloride always has a charge of -1. Crisscross it, you end up with AlCl3. So your final equation should look like this. Al solid added to CuCl2 yielding AlCl3 plus Cu. But this isn't balanced. So you're going to have to go ahead and balance it. When you balance it, you get 2, 3, 2, 3.
What?
Now,
I got 2, 3. Oh, yeah, it's bad.
So, the thing about this problem is that it did not make your life easy by just saying what you have to start with. Instead, they gave you a table. And for the most part, I'm going to keep using this format because it shows me that you're thinking. It says the mass of aluminum is 2.55 grams. Now that I've written my reaction out, I'm going to go ahead and extract information from the table and then plug into my reaction so I can see where things are going. Mass of aluminum, I'm just going to put it under the aluminum. Then it gives me the mass of filter paper and mass of filter paper and copper. Well, I know that filter paper is not part of the reaction, so I'm going to get rid of it by subtracting it out. Am I correct? When I subtract out the mass of filter paper and mass of filter paper plus copper, what mass would I be getting? Mass of the copper. Looking at my reaction, copper is on the product side. So that kind of tells me it seems as though I'm going from aluminum to copper, correct? So I'm going to subtract this out and you should get 3.11. So here it is, 2.55 grams is what we said aluminum is. And then copper, when you subtract out the mass of filter paper and copper with the filter paper, you just get the mass of copper, which is 3.11. So I'm going to go ahead and put that under this, saying that I'm trying to find this aluminum and how much that's going to produce the copper of. This 3.11, raise your hand if you think that this is an actual yield. Raise your hand if you think this is a theoretical yield. Okay, so this is your actual yield because remember, you didn't do anything with the reaction. You just subtracted out the information. You didn't have to do any of the stoichiometric stuff, right? So whenever you don't have to do a really long calculation using the reactants, that's what's going to be your actual yield. So that means we need to find the theoretical yield, and we do so by starting out with what information? What is given to me? What is given? Absolutely, right? That's what I'm given. So I'm going to go ahead and start my reaction with 2.55 grams of aluminum. Now, Jaquez, you asked me what you should be doing. If you got grams of aluminum, what did you tell me I'm supposed to go to from grams of aluminum? To moles of aluminum. And then if I'm at moles of aluminum, then where do I go? Moles of? You're already at aluminum. I'm looking for copper. Hey, quiet down. I'm looking for copper, right? So I have to convert the grams of aluminum into the moles of aluminum by using the number from the periodic table. I'm going to take that and convert it to moles of what, Jamar? I'm going to convert that to moles of what? What am I going to convert to? Yeah, so that, what you just said, is going to take me from moles of aluminum to moles of copper. So it ends up looking like this. Moles of aluminum at the bottom, moles of copper at the bottom. But since you're going from one reactant to another product, you have to use what? You're going to have to use a coefficient from the reaction. So here, looking at my reaction, I got 2 in front of aluminum. I got 3 in front of copper. So I'm going to have 3 over 2. By doing this step, I've taken my grams of aluminum, converted to moles, and then now took it over to moles of copper. But look at my actual yield. It's given in what unit? Grams, right? So I'm not going to be keeping this moles of copper unit. Instead, I'm going to change to grams of copper using the periodic table, and I end up getting this. When you calculate it all out, you get 9.01 grams of copper. You told me that this is going to be what? Theoretical or actual? This is your theoretical, right? So if I'm looking for percent yield, will this go on the bottom or the top of the fraction? Bottom of the fraction. So when you do this, your actual yield is 3.11 that you calculated from the table. You're going to put that over the theoretical that you just calculated. So your final percent is 34.5%. Raise your hand if you got this problem right. I am proud of you because you guys are good to go. Thanks.
See, I did something different.
A student, Ronnie, stop. A student has 200 grams of C7H6O3 to an excess of C4H6O3. This produces C9H8O4 and C2H4O2. Okay, calculate the percent yield if 231 grams of aspirin is produced. Now, they gave you the reaction, which makes your life a lot simpler. And as a matter of fact, it's actually balanced. So, great. Now, I'm just going to pull out information from the problems that's given to you. Add 200 grams of C7H6O3. I'm going to go ahead and write that I got 200 grams of this guy. And I'm going to read this and say, oh, calculate the percent yield if 231 grams of aspirin is produced. So this is 231 grams. But now I need to think, is this my actual yield or theoretical yield?
Actual.
Raise your hand if you think it's actual. Absolutely. This is your actual because it's telling you that it's produced. So that means I need to calculate the theoretical using 200 grams of C7H6O3. So, when I start this, it's going to look something like this. Oh, let's erase some of the ink first. Okay. By doing this, by doing the very first step, you're taking the grams to moles. So at this point, Jasmine, at this point, the grams of C7H6O3 cancels out, and you're left with the moles. You've converted the moles to now the moles of aspirin. Remember, the actual yield is given to you in grams, so I'm going to have to go ahead and convert this to grams as well. So my final answer is 260.9 grams. Guys, calm down. Quiet down. 260.9 or 261. Now, does that go on the top or the bottom? Why does it go on the bottom? Because it's a theoretical yield, I'm going to go ahead and put that on the bottom. And my final percentage is 88.5 or also 89%. Raise your hand if you got this right. Good job.
I got close.
That's
He got
good.
86.
All right.
If it was 86, would you count it?
Did you get one of these masses, Ron?
Yeah, I pulled 130. No, I had 135 right there.
See, I will give you half credit for it.
Oh, okay, yeah, that's
But
good.
I will give it credit, but I want you to get it right next time.
Yeah, I mean,
All right.
I slipped up.
Let's go ahead. As we finish up reviewing the percent yield, let's define these terms. Jamar, so this is when you're going to have to look at the board. Quiet down. Okay. Let's define the following term. The term stoichiometric quantities is wrong. Alright, when you're talking about stoichiometric quantities, it's the reactants that are present in exact amount needed to completely react with each other. So, in the example that we had with the ham sandwich and the cheese, it's like having exact amount of ham, exact amount of cheese, exact amount of bread to make sandwiches without any leftover. The amount of those ham or cheese or whatever that gives you a perfect amount of sandwiches, that's what we call stoichiometric quantities. In chemistry, if we're talking about stoichiometric quantities, that means there is no leftover. Nothing gets wasted in the reactant side. You're going to use up every single reactant that you have. Okay, and if you're still writing, I'm just going to click the next one so you can start. For limiting reactant, it's the reactant that runs out first. But it also is the reactant that produces the smallest amount of the product. So if you think back to last week, we would calculate how much the product we chose to see. We were going to make a prediction about that one product. Between the two possible predictions, we always chose which number? Smaller or greater? The lowest number, right? That's because we assume that whenever the product is in the lowest possible number, that's because the reactant that made you get that number is a limiting reactant. That's why we always choose the lowest number. Now, if the limiting reagent is the reactant that runs out first, then the excess reactant is going to be the one that does not run out first, and there is leftover. Reactant that does not run out or is left over. Okay. So if the reactant, the limiting reactant, is the one that gives you the smallest amount of product, what do you think the excess reactant is going to do? Huh? It gives you the bigger number. So it's the reactant that produces a larger amount of product and these two are determined through calculations.
Hey, so I have a question.
Yes, sir.
So